Welcome to the Deep Dive. Today, we are opening up a remarkable stack of source material dedicated entirely to the technical history and strategic journey of Google DeepMind, specifically their calculated pursuit of artificial general intelligence, or AGI.
And this isn't just a corporate history, is it? It's more like a technical blueprint for how you might go about engineering intelligence itself.
That's a great way to put it. We're tracing the path from the philosophical roots in neuroscience through these incredible algorithms that mastered the world's most complex games.
All the way to solving real-world, half-century-old scientific problems. I mean, things like protein folding.
Exactly. And our focus today is laser sharp. Our mission is to give you the shortcut to understanding the machine learning breakthroughs, the architectural pivots, and the critical engineering implications of all these milestones.
We really want you to grasp the core technical DNA that powered this whole revolution.
Right. The sources chronicle a very distinct, very deliberate journey. The initial concept was it was huge, solving intelligence itself.
And then came the proofs of concept in these highly structured environments. The Atari suite, Go, StarCraft.
Which all culminated in the radical acceleration of scientific discovery with AlphaFold.
The driving goal, though, and this is woven into every single technical decision they made, was to build the world's first general learning machine.
Yes, the emphasis on general is just paramount, isn't it? This system was designed not to master one specific thing, but to have this cognitive breadth, this flexibility.
To be able to generalize. The way they put it was it could be, quote, parachuted into any environment and figure out the optimal controls from first principles.
And that right there, that's the definition of the AGI they were chasing.
What's so striking right from the start is this almost non-negotiable belief embedded in the sources that general intelligence is actually possible.
Yeah, they viewed the human brain as, and this is another quote, the only existence proof we have, perhaps in the entire universe, that general intelligence is possible at all.
So if one proof exists, then replicating it through engineering, it should at least be theoretically achievable.
So we're not just chronicling a series of lucky wins here. We are dissecting a very specific, reproducible technical recipe for achieving superhuman abilities.
A recipe that relies on meticulously structured learning environments and, critically, on scaled computation.
And at the heart of that recipe is reward-based reinforcement learning, or RL.
Yeah, we're going to see how every single breakthrough from DQN to AlphaZero was ultimately unlocked, not just by algorithmic elegance, but by the strategic application of massive, massive scale computation.
Which allowed the whole iterative, self-teaching mechanics of RL to finally function at the capacity they needed it to.
Okay, let's unpack that initial vision, because the ambition was it was truly staggering.
It really was. The goal, right out of the gate, was solving all of intelligence. To create an intellectual tool so powerful it could solve the world's most complex scientific problems.
The founders didn't shy away from comparing this to civilization-altering developments either. No, not at all. They saw AGI as potentially bigger than the internet, bigger than mobile telephony.
More like the advent of electricity or even fire.
Exactly. It was about creating a tool that fundamentally changes humanity's intellectual limits and its potential for acceleration.
And the origin story is so fascinating because it's deeply rooted in computational neuroscience.
Right. One of the founders deliberately studied neuroscience to, as he put it, get inspiration from the brain for AI.
So that was a foundational architectural choice right there. They were seeking to mimic the underlying biological structure of learning and memory, not just building a faster sort of conventional computer.
But that fixation on biological inspiration created an immediate challenge, didn't it? The sources call it the problem of academic context.
Oh, yeah. Around the time DeepMind was forming, talking about AGI was almost career-limiting.
AI was often dismissed as an embarrassing word in serious academic circles, especially after the so-called AI winter.
And all the prevailing research was focused on these narrow, incremental, provable gains.
Which is completely the opposite of the AGI project. I mean, if your goal is AGI, you need decades, not semesters.
You just can't run those long, risky, expensive challenges within a typical academic setting.
And you certainly can't do it in a standard Silicon Valley startup that needs immediate product monetization and, short-term quarterly results.
AGI demands moonshot thinking. It doesn't work with short-term metrics.
So the first strategic necessity was securing an environment, a company essentially, where they could commit to this huge high-risk plan.
And the pitch was basically, We're going to try to do artificial general intelligence. We have some ideas on the approaches, but we need huge amounts of money, huge amounts of risk, and lots of compute.
A tough sell.
A very tough sell. But that focus on generality was the key foundational philosophy. They believed if they could build one system that solved all of intelligence, it would be the ultimate proof.
They really stressed the word general because historically, the greatest AI achievements, things like Deep Blue, were incredibly specialized.
Right. Deep Blue was a genius at chess, but it couldn't learn to play checkers. It couldn't play Atari.
Whereas true intelligence, they argued, is the ability to learn to do many different things.
This philosophical commitment led directly to the funding challenge.
Of course, when you're pitching, we're going to solve all of intelligence, investors are, understandably skeptical. They're asking, what's your product? What's the revenue stream?
The sources emphasized they weren't looking for conventional investment. They were looking for people who thought the idea was simply really cool.
Investors who were willing to bet on the time scale of a scientific revolution, not a 5-year IPO window.
But even with that initial backing, the sheer ambition meant they quickly hit a computational wall.
Every RL approach they planned required just massive iteration, something that simply wasn't feasible on typical startup infrastructure.
And that's what dictated the strategic pivot, the acquisition by Google.
The Google acquisition wasn't really about monetization, was it? It was a technical resource acquisition driven by pure necessity for scale.
The founders realized that getting access to Google's, virtually unlimited compute infrastructure would, quote, accelerate our time scale to AGI massively.
It's incredible. They essentially undersold the company's immediate commercial value because, for them, the mission timeline was just too critical to waste time on conventional fundraising.
And they secured a very rare, crucial agreement. Joining Google, but running independently in London, maintaining a culture optimized for pure research and breakthroughs, shielded from those typical commercial pressures.
Which immediately resolved the fundamental technical bottleneck.
Absolutely. If you want a general learning system powered by RL, you need a high-fidelity environment where it can train, iterate, and fail spectacularly millions of times a day.
And Google provided that engine of computational resources to make their theoretical algorithms a reality.
So this move allowed them to connect their initial theoretical ambition, that biological inspiration combined with general learning, with the scaled resources necessary to move from paper to prototype.
The philosophical commitment to generality was now finally matched by the technical commitment to scaled iteration.
Okay, let's initiate our first neural signal check. We really need to get into the nuts and bolts of the core technical framing here.
Yeah, because everything that follows really hinges on understanding this agent environment loop and the specific engineering required to make it stable.
So at its foundation, we're talking about the basic reinforcement learning setup. You have the agent, the DeepMind AI, and the environment it interacts with.
Which is usually a game screen, right?
Exactly. And the agent's mission is deceptively simple. Optimize a goal. It has to learn the controls, the rules, and the consequences of its actions entirely from first principles.
Based solely on the rewards or the scores it receives. It's true learning from experience.
The selection of games as training grounds was a very disciplined technical decision. They chose the Atari suite because it provided a massive generalization test.
Right, they required one algorithm using the same brain, the same neural network architecture, to play several dozen different games.
And the agent was designed for end-to-end learning. It was only fed raw pixels from the screen and the score.
It started with zero domain knowledge. It didn't know what a paddle was or a ball or even what the objective was. It had to build its entire understanding of physics and causality completely from scratch.
So the specific breakthrough centered on the Deep Q network, or DQN.
And this wasn't just a slight improvement. This was the first time an old, theoretically sound method Q learning was successfully combined with deep learning at a functional scale.
So break that down for us. What's Q learning?
Q learning works by estimating the Q value, which represents the maximum expected future reward for taking a specific action in a specific state.
Okay.
And the deep learning component, the neural network, is what allowed that Q function to scale up to handle these complex, high-dimensional inputs like raw pixels.
Because historically, Q learning couldn't handle the complexity of an image, right? It could only handle small, discrete state spaces.
Exactly. But combining the two created massive technical challenges. Standard Q learning is notoriously unstable when you integrate it with a big function approximator, like a deep neural network.
Especially when the training data is highly correlated. The system would often just forget what it just learned, or its estimates would just wildly diverge.
And this is where the core engineering genius of DQN truly lies, and it's something that's often glossed over. DeepMind introduced two critical stabilization mechanisms to break that data correlation.
The first one was experience replay.
Right. So the agent doesn't just learn from the last action it took. It stores this vast memory bank of past experiences, state, action, reward, next state.
And during training, it samples small batches randomly from this buffer.
And that random sampling is absolutely key. In standard RL, the agent's actions are highly correlated. If you move left, your next state is highly likely to be the state slightly further left.
So if you train a neural network on a continuous stream of that correlated data, you get catastrophic forgetting.
Precisely. By randomly sampling old and new experiences from the replay buffer, they broke this autocorrelation, ensuring the network saw a diverse, independent distribution of data. That's what stabilized the training process.
And the second stabilization mechanism was fixed Q targets.
Yeah, this is also crucial. When you're training a neural network in a regression problem, you need a stable target value to move toward.
But in standard Q learning, the target Q value, the estimated maximum future reward, is constantly changing as the network updates.
Which leads to this famous chasing your own tail problem. The estimate is chasing a moving, unstable target, and it just leads to divergence.
So DeepMind fixed this by periodically freezing the parameters of the network used to calculate that target Q value.
They created a target network that was only updated with the online network's parameters every few thousand steps.
So that provided a stable, non-moving target for the agent to regress towards for a substantial period.
And that finally allowed deep Q learning to converge reliably. Those two mechanisms, experience replay and fixed Q targets, are the true technical breakthrough of DQN.
But even with these tools, there was the famous palm struggle.
Oh yeah, the sources describe a period of really high anxiety. The agent was only told score is good, and it just could not figure out how to move the paddle in pawn.
For weeks, the agents were just oscillating randomly or ignoring the controls.
They were on the brink of thinking, maybe we're fundamentally wrong about our RL approach. We can't even solve Pong.
And then came the aha moment, which was really fueled by the computational resources Google provided.
So instantly, autonomously, the agent connected the pixels, the reward, and the necessary action to move the paddle and score its first point.
And from that initial discovery, within 3 months, no human could beat it.
This single event proved the whole thesis. End-to-end learning from raw pixels to complex control was possible, all thanks to that stabilized DQN architecture.
And the generality immediately proved out, didn't it? It validated G and AGI. They moved to breakout.
And initially, it misses the ball. After 300 games, it's playing at a human level. But when they left it to iterate for another 200 games, something profound happened.
The agent found the optimal strategy, a completely emergent, novel behavior.
It wasn't programmed with concepts like tunneling or trapping. It simply learned to exploit the game physics.
It dug a tunnel around the side of the screen to send the ball behind the wall, trapping it to rack up points unimpeded.
And that demonstrated a kind of computational creativity that went way beyond simple rote memorization or reactive policy. The agent had developed a deep causal model of the environment and found a globally optimal solution to maximize its reward function.
Entirely on its own. The DQN architecture, stabilized by those two critical engineering tricks, had delivered general learning. So with the DQN success establishing that RL foundation and the massive compute engine secured via Google, the next target was Go.
Which was considered the holy grail of artificial intelligence and, the true pinnacle of strategic depth.
From a technical standpoint, Go was just orders of magnitude harder than chess.
Oh, absolutely. Chess has a branching factor of around 35 possible moves per turn. Go, on the other hand, has an average branching factor of 250.
Which means the number of possible board configurations is astronomically high.
Far exceeding the number of atoms in the known universe, which is why it earned the label incomputable. Brute force, or traditional search methods, were completely useless.
So the previous Deep Blue approach, which relied on evaluating massive static search trees and using hard-coded expert knowledge,
it just falls over when faced with Go's complexity. A totally new architecture was necessary.
And this led to AlphaGo's hybrid training methodology. It needed to blend the power of deep neural networks with advanced search techniques.
Specifically, Monte Carlo tree search. or MCTS, which explores the game tree by sampling plausible paths rather than doing exhaustive searches.
So the hybrid approach had two very distinct phases. First, imitation learning.
Right, AlphaGo was initially trained on a massive database of 100,000 games played by strong amateur players.
The goal there was just to teach it human strategy and heuristics, to get it to mimic expert play and give the network a rapid, high-quality policy to start from.
And then came the crucial phase, reinforcement learning and self-play.
After the imitation learning, AlphaGo entered its own iterative loop, playing millions of games against various versions of itself.
The policy network determined where to search, and the value network estimated how good the board position was, guiding the MCTS algorithm much more effectively than previous methods.
And this cycle of self-improvement was the real engine of its power.
This training all culminated in the match against Lee Sedol, the reigning champion. And this is where the system demonstrated true, original insight that just shocked the human Go world.
The moment everyone remembers is the surprise move 37 during the second game.
AlphaGo played a shoulder hit deep in the center of the board, and the professional commentators were just aghast.
They instantly dismissed it, didn't they? They said it was a huge mistake, a move no human champion would ever consider in that situation.
But was that just computational creativity, or was it a fluke? The sources show it was definitely the former. AlphaGo's internal analysis, powered by its value network and MCTS, determined that move 37 held a strategic advantage over the entire duration of the game.
It was a globally optimal move that human intuition, constrained by thousands of years of established conventions, just couldn't see.
And the internal calculation was critical. AlphaGo itself calculated only a 1 in 10,000 probability that a human player would have chosen that move.
It demonstrated that this scaled RL architecture, guided by MCTS and deep networks, could uncover a depth and strategies that human knowledge had simply never fully grasped.
That moment, and the subsequent victory, was recognized globally as a Sputnik moment for AI.
Governments, particularly China, recognized immediately that a new level of technical capability had arrived on Earth, launching this massive global race to replicate and surpass the achievement.
But DeepMind immediately recognized the limitation. AlphaGo still relied on human data to bootstrap its learning.
Which led to the next step, the ultimate technical evolution, AlphaZero.
AlphaZero represented a radical technical simplification. It was a much more elegant approach, as they called it, stripping out all human knowledge entirely.
The zero means zero human knowledge in the loop. Now, 100,000 games of expert data.
This was a total paradigm shift. AlphaZero was given only the basic rules of the game chess, Go, or shogi, and it learned exclusively from its own self-play.
It became its own teacher, bootstrapped completely from scratch using a single, uniform architecture that was applicable to any two-player perfect information game.
And the efficiency and scale were just breathtaking. AlphaGo took months of training on GPUs and human data.
AlphaZero could start playing randomly in the morning and be at a superhuman level by dinner.
It surpassed all previous Go programs, all previous shogi programs, and it became the strongest chess engine ever recorded, all using the exact same algorithm.
What's truly fascinating is the style it developed, too. When they applied it to chess, the system abandoned human-learned heuristics like, protecting your material at all costs.
It's often preferred these deep positional sacrifices, sacrificing a queen for long-term spatial or initiative advantages, a style that was deeply unsettling and revelatory even to grandmasters.
It revealed that there was, quote, even more depth than we thought in chess.
Okay, so let's do a neural signal check, the core technical implication of AlphaZero.
This proved that generalized intelligence can be bootstrapped entirely from self-experience without any reliance on prior human expertise.
And all using one highly generalized algorithm. It just accelerated the learning curve dramatically, condensing millennia of strategic evolution into a few hours of compute time.
The unified architecture applying equally well to chess, Go, and shogi is really the definitive proof of AGI generality, at least in highly complex, structured decision systems.
But as powerful as AlphaZero was, achieving true AGI demand systems that can move beyond these structured, perfect information environments.
Right. Intelligence has to be flexible enough to solve novel problems and interact with messy, fluid, and partially observable environments, like the real world.
And that was the focus of the next phase of their research.
DeepMind began by seeking inspiration from early human cognitive development, how we develop logic, navigation, and memory just by interacting with physics.
Which led to the creation of simulated environments as a training ground.
The technical premise was pretty simple. Just mimic childhood learning. They created these virtual recreations for humanoid agents. For instance, a robot agent was rewarded simply if its center of gravity rose.
So the agent had to learn how to stand up and walk.
And the beauty of the reward-based RL approach is its purity, isn't it? The agent purely focused on maximizing that reward signal didn't just learn to walk forward.
In some iterations, it found that shuffling or even walking backward was good enough or computationally easier to optimize the score.
It really highlights the raw and sometimes strange output of a system that's just obsessively optimizing a clearly defined but complex function.
A far more complex physical test was the parkour challenge.
Yeah, in this one, they trained a simulated robot to run forward across diverse, procedurally generated terrains, obstacles, gaps, stairs.
And the only reward was forward velocity.
The algorithm autonomously figured out the highly complex joint movements necessary to balance, to leap, and to recover balance. It's a pure demonstration of the power of reward-based RL solving complex biomechanical control problems without any explicit programming of physics or motor control.
This successful handling of physics and simulated embodiment leads us to the grand challenge of complexity and partial observation. Real-time strategy. StarCraft.
Exactly. To achieve generality, agents have to handle complex visual input, manipulate thousands of simultaneous variables like units and buildings, and deal with missing information, the fog of war.
And StarCraft is really the epitome of this multifaceted challenge. It tests long-term economic planning, high-frequency motor control,
Yeah, clicking on units.
predictive modeling of your opponent's behavior, and resource management all happening simultaneously.
So let's clearly define the technical constraints of StarCraft versus Go chess. First, decisions are continuous, not discrete turns.
Second, the action space is just vast. In chess, you have maybe 35 legal moves.
But in StarCraft, an action requires selecting a unit, choosing an action like move or attack, and then selecting a precise coordinate on the map. The action space is enormous and continuous.
And third, and most importantly, is partial observability. You can't see your opponent's base or their army unless you scout it.
So you have to make decisions based on memory, on inference, and on incomplete, real-time visual information.
This confluence of complexities required a completely different technical approach from the policy and value network used in AlphaZero. The challenge shifted from finding the optimal static strategy to finding the optimal sequence of actions given a highly variable, partially known state.
This is where AlphaStar's methodology drew direct inspiration from architectures that were successful in sequential modeling.
They applied principles found in large language models, or LLMs, and transformer architectures. But it's not simply predict the next move, which would be impossible given the action space.
So what was it then?
Instead, AlphaStar was trained to predict the next sequence of microactions, given the current visual screen state and the agent's long-term memory of the map. What was scouted? What resources are available?
So it's using a type of transformer architecture to handle the long-term dependency inherent in strategic planning.
Exactly. A decision made 5 minutes ago, like building a specific resource structure, has consequences right now.
The analogy to LLMs is really about sequential decision-making in a high-dimensional visual environment. LLMs predict the next word in a sequence.
AlphaStar predicts the next unit command in a sequence, taking into account the history and context.
Plus, the sheer frequency of actions required them to manage massive action-per-minute rates. Humans struggle to maintain 300 APM.
Right, and AlphaStar needed to process and execute thousands of precise actions over the course of a long game.
The initial results were humbling, though. AlphaStar struggled against even amateur players because it couldn't manage the real-time constraints and the micromanagement requirements.
But through massive iteration and a competitive multi-agent league structure where different versions of AlphaStar competed against each other, the system learned.
It learned to manage economic scaling, diverse unit compositions, and real-time defensive and offensive maneuvers.
Eventually, AlphaStar beat top-level professional players.
And the key technical achievement was proving that an RL agent could not only handle the vast continuous state and action spaces of a complex environment, but could also operate and excel under conditions of partial observability.
Making strategic decisions based on probabilistic inference rather than perfect knowledge.
This confirmed a critical step on the path to AGI. The architecture could adapt from the philosophical discovery required in turn-based games to the high-frequency, complex, strategic execution required in a fluid environment. So the ultimate goal, as they stated from the very beginning, was never just games. It was to use AI as the ultimate intellectual tool to solve real-world scientific problems.
And the first major target was the protein folding problem, one of the grand challenges of biology.
From a biological and computational challenge perspective, this is just vital. Proteins are the nanoscale machines of life antibodies, enzymes, structural components.
And the problem is predicting the complex, functional 3D structure of a protein from its simple 1D amino acid sequence.
Solving this would be revolutionary for drug discovery, for understanding diseases like Alzheimer's, and for engineering novel biological solutions. It has stumped scientists since the 1960s.
What makes this so fundamentally different from the game-based RL problems is the data constraint.
Right. In Go or StarCraft, the agent can generate infinite training data via self-play.
In protein folding, you rely on a fixed, sparse data set. And that data set has been built painstakingly over a half-century of time-consuming experimental methods like X-ray crystallography.
Methods that can take months or even years to determine a single structure.
And that's a crucial machine learning distinction. The model can't just play a billion games against itself. It has to learn deep, complex physical and biological rules from relatively sparse, expensive, and hard-won experimental data.
So this necessitated a shift away from pure RL to a system that could integrate domain-specific knowledge and geometric reasoning.
To prove their thesis, DeepMind entered CASP, the critical assessment of protein structure prediction.
Which is known as the Olympic Games of Protein Folding. Teams are given 100 unknown protein sequences, and their predictions are rigorously scored against the experimental gold standard structures.
A score over 90 on their metric is considered a structural solution.
And the first attempt, in CSRP-13, resulted in initial failure and humility.
Yeah, they threw their standard, obvious, sequence-to-sequence deep learning ideas at the problem, and the predictions were just poor. The problem, as the sources noted, laughs at you.
The predictions were not significantly better than existing, slower computational methods.
And the key realization was profound. Naive machine learning was insufficient. They learned that while they were the best in the world at RL, the field they entered, structural biology, was one the entire world was still struggling with.
So they needed to stop treating it like a standard computer vision problem and start treating it like a physical modeling problem.
This failure spurred a crucial technical shift. They realized they needed to incorporate explicit domain knowledge and understanding of physics, geometry, and biology directly into the AI architecture itself.
This wasn't about more compute. It was about better structural modeling.
Which led to the formation of the AlphaFold Strike team and technical refinements. The team was reorganized to integrate computational biologists alongside the machine learning experts.
And they began rewriting the architecture to focus on geometric deep learning, specifically modeling the relationships and distances between pairs of amino acids in 3D space.
The architecture shifted dramatically. Instead of a standard sequence-to-sequence prediction, AlphaFold 2 used a novel approach, incorporating mechanisms similar to invariant point attention, or IPA.
Which allowed the network to simultaneously reason about the physical coordinates of the atoms and the amino acid sequence.
Right. This provided a way for the network to understand 3D structure prediction that was independent of the overall orientation of the protein, a critical invariance requirement for physics.
And one specific technical advancement that drove enormous quantifiable progress was the precise modeling of adding side chains. Why was that so important?
Well, the polypeptide chain, the protein's backbone, dictates the rough shape. But it's the 20 different types of amino acid side chains that dictate the precise local chemistry, the bonds, the interactions that stabilize the final functional structure.
So predicting the backbone shape is only half the battle.
Exactly. Predicting the precise orientation and interaction of those side chains is necessary to achieve biological accuracy. By incorporating this domain knowledge into their loss functions and data representation, they gave the model the necessary tools to navigate the subtle physics that stabilize the final structure.
They were now using physics as a guide, even if their initial understanding of the physics was flawed, to constrain that massive search space.
And the payoff was spectacular during the triumph, CASP-14 in 2020.
The results were acknowledged as finally providing a robust, highly accurate solution to the protein folding problem after half a century. AlphaFold's accuracy was amazing, achieving an unprecedented median score.
It beat the second-place team by nearly 50%. The structures were deemed by external experts to be practically useful to biologists.
Meaning they were accurate enough to base real-world drug design on.
And the technical acceleration achieved was stunning. During that humbling CASP-13 attempt, it took AlphaFold a day or two to fold one protein.
By CSP14, using the refined geometric architecture, the system was folding hundreds or thousands a second.
They achieved orders of magnitude faster speeds while simultaneously achieving biologically meaningful accuracy.
The final revolutionary step was the real-world impact and scaling. Once they possessed this validated capability, the scale became immediately apparent.
The realization was, we can easily predict all known sequences in a month.
And this led to the landmark decision to fold and release the structures of 200 million proteins, the entire known proteome of humanity and nearly all sequenced organisms, to the scientific community.
Making the models in the database completely open source. This is a profound gift, accelerating biological and chemistry achievements globally.
They recognized that the instant the AlphaFold library went live, they were no longer the most important people in the AlphaFold story.
The world scientists were now equipped with the ultimate tool.
So what we've tracked here is the systematic technical advancement of AGI capabilities, following a really clear, structured path.
It moved from a stabilized DQN agent learning complex control from raw pixels
To AlphaZero, discovering novel, optimal strategies in games like Go and chess, demonstrating real computational creativity.
and finally solving one of biology's grandest, most intractable problems with AlphaFold.
This journey really underscores that the pace of generalized learning innovation is accelerating like a boulder rolling down a hill.
The key technical ingredient has always been this relentless pursuit of generalized learning algorithms, culminating in that zero-knowledge model of AlphaZero, and strategically coupling that architectural elegance with massive targeted computation.
Which is what unlocked scientific discovery in these complex, real-world fields.
That initial shockwave from AlphaGo, a so-called Sputnik moment, launched a massive global race based purely on recognizing that reproducible, scaled RL architectures had arrived.
And the technology demonstrated that complex intellectual discovery could be automated and scaled.
So, the final implication for the learner. The DeepMind journey confirms that AGI is on the horizon, not as some theoretical novelty, but as a result of measurable, reproducible technical breakthroughs in generalized learning architectures.
The core challenge, then, for the next generation of engineers is understanding not only how to build these sophisticated systems, but how to responsibly apply technologies that are scaling far beyond typical human intellectual speed limits.
And the entire development process just shows the power of integrating fundamental scientific principles, whether from neuroscience, game theory, or physics, directly into scaled machine learning models.
It's the convergence of that deep structural knowledge and generalized optimization that yielded the greatest results.
Which brings us to a provocative final thought. If AlphaFold solved a problem that thousands of smart people couldn't crack for decades by incorporating physical domain knowledge into deep learning, what other currently incomputable scientific problems are now ripe for solution?
Things like designing entirely new, complex materials with predefined properties or modeling the incredibly complex interactions that lead to systemic health failures.
Exactly. What problems are now solvable using this exact same recipe of generalized reinforcement learning architectures guided by domain-specific geometric modeling? The limit is no longer the problem's complexity. It may only be our imagination in defining the reward function.